Hey everyone, welcome back. Today we're going to talk about the wave nature of light. So, treating light as a wave, as the title suggests. This is part one of three total videos or note sets on this topic that we're going to cover. So, first of all, second on three different ways of thinking about light. Last chapter, when we studied geometric optics, we pretended light was a ray, which is not really describing the true nature of light, of what it is. The other two, a wave and a particle, yes, that is describing the true nature of light. But the ray thing, the geometric optics, is more like a useful tool. So if we pretend like light propagates as rays, we can explain things like mirrors and lenses and what we see when we look into a mirror or when we see something through a lens. So that's more of just like a useful trick that we can do. The next two chapters we're going to look at are physical optics and quantum physics. The focus for this week and the next couple weeks is physical optics, which is treating light as a wave. Then we'll look at quantum, where we can treat light as a particle. And the really cool thing, the really interesting thing in physics is that we have experiments that prove that light is a wave. And we're going to talk about those in the next section of notes. So if you aren't convinced that light is a wave, check up for part two. However, at the same time, we also have other experiments that prove that light is a particle. That's quantum physics. So what do we do with that? The answer is even more exciting than just, oh, light behaves like a wave and light behaves like a particle. The world of quantum physics gets even more exciting than that. I would try to contain my joy for a little bit until we get there. But today, light is a wave, model number 2, I guess. 2-ish, depending on how you calculate it. Anyway, light is a wave. So there's some basic stuff about all waves that you're going to have to remember or learn, because as a wave, all of this stuff that's true for waves is true for light as well. Couple different types of waves here. Mechanical waves are any waves that require a physical medium. Those are things like waves on a slinky, waves in the ocean, or sound waves. The whole thing from the movie Alien, in space, no one can hear you scream. That's because in space, there are a couple atoms kind of here and there, but there aren't enough atoms to propagate sound waves. Sound is a mechanical wave. You need air between you and the person you're talking to vibrate back and forth to actually transmit that sound. So when you're hearing sound, you're hearing air molecules that are smashing into your eardrums, and that's getting turned into a signal by your brain. But long story short, mechanical waves do need a medium. Light, which we are concerned with here, is not a mechanical wave, which means it does not need a medium to propagate. It can go through a vacuum. Any number of ways of proving that. We can get a vacuum if you want. We have a vacuum pump at school. If you really want me to, I can create a vacuum and shine a flashlight through it. The flashlight goes through it. Also, see the sun. Don't look at the sun, but the sun, the light from the sun reaches Earth, passing through the vacuum of space. Cool. So light is also called EMR, or electromagnetic radiation. We'll talk about the whole electromagnetic spectrum. But for now, know that that's visible light that we can see, but also infrared, UV, gamma rays, X-rays, radio waves, microwaves, all those different things are light. They just have different wavelengths and frequencies. So here's an important fact about all waves. Waves transfer energy from one place to another with no net movement of matter. If you're talking about a mechanical wave that's propagating through a physical medium, the particles are moving, but there's no net movement of particles. Some examples here. I don't know if we're going to watch this whole thing, but this is a giant stadium wave at a NASCAR thing or something like that. And if you want to see if they actually make it all the way around, pull up the notes. You can see it. That's an example of a mechanical wave propagating through a medium. Here's some more mechanical waves here. This is a wave pool, a giant wave pool, actually. Um, it won't let me skip ahead here, so we'll just watch it. Looks like fun. Anyway, but what those waves have in common is they are transferring energy from one place to another, but there's no net movement of matter. We'll see an animation in a few slides where water waves, particles are actually traveling in little circle or circle-ish shapes, so they end up where they started. But energy gets pushed from one place to another, but you're not taking matter and piling it up. You might feel that if you've ever been to the beach or in a wave pool, you can feel that the wave, as it passes, sort of pushes you forward, but then you also feel like you get sucked back a little bit. Here are the parts of a wave. Wavelength, it lists one complete length of the wave. You can measure from any point to the next time that point occurs. So here you're going from crest to crest. You can measure it from trough to trough or whatever to whatever, as long as you go to the next time that point happens in the wave. Amplitude is the total displacement away from the 0 point, if you want. And crest and trough, I guess that's all of them. Some wave equations you may remember from last year. Period is the amount of time it takes for one full wave to pass by a given point, or for a wave to go through one complete cycle. Period uses the symbol uppercase T. So because you're measuring a time, the time it takes for one full wave, the units of period are seconds. And the equation that relates period and frequency is period equals 1 divided by frequency. So that shows you that frequency has to have units of 1 over seconds, inverse seconds, also known as hertz, capital HZ. Frequency is the number of waves that pass by a given point per unit of time. So lowercase f on that. Here's another one. This works for all waves. We're going to use this one maybe a little bit more frequently for light, but it works for any wave. The wave speed, meters per second, is equal to f times lambda, frequency times lambda. Notice that the units work out there. Frequency is 1 over seconds. Wavelength, obviously, is measured in distance, so meters. 1 over seconds times meters gives you meters per second. Two very awesome videos. I'll throw these in the Schoology folder for this week. One of them is how you can use Peeps, the little marshmallow chick things, to measure the speed of light in your very own house with your very own microwave, which is just brings me tons of joy. And the other one is a Veritasium video about how we may technically not know the speed of light, and the speed of light may not be the same in all directions. If that interests you at all, check out that video. I watched it a couple weeks ago and it totally blew my mind. Oh, that's trying to play that one. That's your preview. Oh, and it's trying to play that one too. Neat. That's your little teaser trailer for those. Unintentional. Two different types of waves. These are longitudinal waves. So you can see in a longitudinal wave, the particles of the medium are moving back and forth, but their movement is in the same direction as the wave. So waves are going from left to right, and the particles are also moving in that same x direction, if you will. Areas where there are high density, or where the wave looks like it is here, are called compression. Rarefaction is in between. But if you pick any particle, you can see there's no net movement of particles. You can see the waves move all the way across the screen here, but each particle just goes back and forth. So no net particle movement there. Transverse waves, same is true. There's no net movement of particles. But if you pick a particle and focus on it, how about this little lost particle down here all by itself? It's going up and down, but the movement of the wave is side to side. So for transverse waves, the displacement of the particles is perpendicular to the direction that the wave propagates. And you can see that if you sort of pick one of these wave humps and you follow it, it looks like it's going from left to right. Light is a transverse wave. It doesn't have these, light doesn't have particles because it doesn't need a physical medium to propagate through. it actually has oscillating electric fields and magnetic fields. You don't need to know all those details yet, but the direction of those oscillations are perpendicular to the direction of the wave propagation. Here's water, so you can see the waves move. This is sort of a more complicated example, but it's a mechanical wave. Each particle moves in a little circle. Those circles get smaller as you get deeper and deeper down into the water. But again, there's no net movement of particles. Next is the idea of superposition, which simply put just says waves can add together, either constructively or destructively. That's going to be a huge idea in explaining all the bright and dark spots we're about to see in the next two note sets here. But just think about waves on a slinky. Or this works with sound waves, this works with light waves. Anything that is a wave will do this. And this is actually how Thomas Young figured out that light was a wave back in the early 1800s. What? Super cool. But you can see here when we take two waves and crash them together or try to put them in the same place at the same time, they will add together to either give you a bigger wave or they can give you a smaller wave or no wave at all, depending on the circumstances. So here's the fast big wave, overtakes the little one. You get a super wave for a minute, and then the waves continue at their speed and just keep going the way they were. Here's more. This sort of shows you what's happening with a standing wave. But if we take a blue wave going to the right and a red wave going to the left and add them together, that gives us a standing wave where we have these sections where you see like right where the cursor is here, there's no movement. That's a node. And then in between, there's an antinode. That's where you have the maximum movement. Constructive interference like this happens when waves are in phase with each other. So these two waves are completely in phase. Crest lines up with crest to give you a super crest. Trough lines up with trough to give you a super trough. And then this point of zero amplitude lines up, which corresponds with a point of zero amplitude. If you take the red wave and shift it off by exactly half a wavelength, now we're trying to add them so that the crest lines up with the trough. Those two cancel. Our little node here lines up with the other node, and then trough lines up with crest to give you no amplitude whatsoever. This is like two waves opposite on the slinky going across, canceling each other out when they meet. You can do this with physical waves. Obviously, you can do this with sound. That's actually how noise canceling headphones work. They generate a wave that is out of phase with the background waves that you're hearing, and they literally cancel the sounds out, which is pretty cool. And we'll see in a little bit, you can do this with light waves too. Last thing with our little wave intro is something called Huygens principle. I think that's how you pronounce it, but I don't know. Start a little war in the comments if you don't think it should be pronounced that way. But this is basically a way of sort of predicting where a wave is going to be in the future. And this is it in writing in sentence format. I'll show you some pictures that will probably make a little bit more sense. But simply put, it says that every point on a wave is a source of wavelets, which are tiny little ripples emanating waves. Think about dropping a single pebble into a pond. And the waves are going to spread out just like ripples in a pond. And the new wave front is tangent to all these little wave fronts. If that's super confusing, let's just look at a picture. So here's a wave that is completely straight. And if you imagine a completely straight wave going through water, it's just going to be in a straight line as long as it doesn't hit anything. So if you imagine a bunch of little points on here, each one of those is a little spot where you're dropping a pebble in the water, and those ripples go out from the pebble. And in the future, some of those ripples will be here. If you draw a tangent to those, you'll see a new straight line. So straight waves propagate straight. Here's a curved one. If you imagine each little dot as a source of pebbles, waves spread out, ripples spread out in a circle, and the new wave front is tangent to all of those little mini wave fronts, which you can see just like if there was a big pebble here, you get circular propagation like that. These examples are not that exciting, but interesting things happen when you either put an object or a slit and then pass a wave through it. So here we can see we've got these wave fronts that continue out as we would expect them to. But if you look at these little pebble point sources at either edge of the slit, the wave fronts curl around and they go straight all the way to the walls of the slit here. And if we trace out using Huygens principle to go further and further into the future, the wave will actually bend around these corners. So if you have corners or slits of the right magnitude, you can take a wave, send it through the slit or send it by the corner, and this says that the wave will actually bend and go around the corner. Obviously, this only works with some things. The size of the corner, the size of the slit has to be more or less proportional to the wavelength. And that's why you can hear someone who's standing around the corner from you, even if you're outside and there's nothing to bounce their voice off, but you can't see them because the corners are way too big for light waves to bend around, but sound waves have a longer wavelength, so you can actually hear people around corners. All right, that'll do it for part one. If that was exciting, I really enjoyed it. Hopefully, I'll see you soon for part two.